record button, which means you don't want to say anything that you don't want to have recorded, I guess. And so that's good. And let me show you my talking points for today. Unfortunately, I was in a meeting that I won't talk about the meeting that I was in, but I mean, we're going to be fine. But I would have much rather been doing some more preparation for today's lecture than being in that meeting. But anyway, that's where we are. And so here is a thing, and I don't know if I shared screen, so let me go back and try that again, because I think I didn't share the screen. Okay, so now I'm going to share the screen, and I'm going to share the screen that is called Applications Screen. And now, eventually, not yet, but very soon, I will show you a PowerPoint slide, and it says talking points. And this is what I plan to do during our time today. The first 4 bullet points are just things that I want to talk about. So I'm going to talk about them just a little bit, and certainly you can ask questions about those, but those are sort of administrative things that I think are worth covering off. So we'll talk about those, and I'll say some things, but then I will go into what has sort of become my custom, and I think it's a good custom, at least for where we are online this way, is for me to do some polling. And I will ask each and every student who is here right now, and I will ask you, how are you and yours doing? Just to, general. I got to be careful. I don't want to call it a wellness check, but just saying, hey, how you doing? But then also ask if you have any questions or concerns or comments or issues, whatever, that you want to share with the group. So anyway, I will do that before we start on content. And then content, and I didn't put it here, but and I'm not exactly sure. I need to go back. I think you're watching me make this chart in real time, which is fine. But I planned to talk about Bernoulli equations today. I plan to talk about separable. No, that's not what I want to say. Okay, it is not separable equations. It is exact equations. Depending on who you studied calculus 3 with, you might say you know about those. But anyway, we'll talk about exact equations. And then we will talk also, perhaps, we'll see if we get that far, about Clairaut's equation. And actually, that would be a really good period if we got all that done. And I'm not really worrying about if we don't get all that done because of, well, I'm just not worrying. It'll be fine. Okay, now, so I'm going to then now begin. And let's see, let me share this so it's actually legit with what we're doing. Okay, and then I'm going to go to the, for some reason, oh, I know what it's doing. It's not. Okay, now I will go back to the, there we go. Okay, so I'm going to talk about tools for rules. You may or may not know this, but the College of DuPage is a very rulish institution. There's a lot of rules, and in this COVID area, we're having a lot we're having a lot of rules too. And I've talked with you at about great length about this in videos, and you've seen things and everything. I don't want to talk about it, except there is a brand new tool that I think you won't find useful. And so that's the very first thing I'm going to do, is share this with you. And as nearly as I could tell, this was not shared with you. Okay, so there's a friend I have who is the Dean of Students, and her name is Nathania Montez. Anyway, this is an email that I just got from her. Okay, so this is late breaking news, and she in fact entitled this email something like, "Oh, new tools." So anyway, I'm sharing this tool with you. So I know I'm reading to you, but I just will read to you. I am pleased to announce that students are now able to check their own cleared, not cleared status in My Access. And where the student has to go is you have to go under Academic Profile and under My Profile. And there's some sample views that I cut and pasted and put below here so we can look at these and things like that. Now, what I had told you previously, and it's still true, is that I also have this information on my class roster. And before we meet together for the first time face to face on February the 7th now, um, as part of my preparation, I'm going to look and I'm going to say, well, who is cleared and who is not cleared, because that's something I'm having to do. Because the college wants faculty to do this, and I am a team player. But I was very concerned that if there, and we have no Susie Smith in this class. In fact, we have no John Doe in this class. So let's just talk about John Doe. Suppose that John Doe, and the administration even gave me a form to hand to John Doe and say it, and the form basically says, you are not cleared by the college. You need to fix that. You're not in compliance. And I don't want to, in the classroom, go up to some student and hand them a form and everybody says, oh, that student is non-compliant or something like that. That just isn't any good. So what I'm going to do, and I'm saying, oh, this is okay. I will just make copies of that for everybody in the class. But then what I will do as part of my preparation is I will write across the top, either you show up as being cleared or not cleared. And if I hand it to you and it just says you're cleared, you say, well, that's good. And maybe I'll, whenever I call out your name, you'll raise your hand and I'll say, oh, that's what you look like. And then I will go there and give you the form, and that is all good. So that's how that can work. And if you're not cleared, I'll write, hey, you're not cleared. You need to fix this. And you could talk to me after class or whatever about how to fix it. But actually, you should understand that. Now, I was concerned at the time, and I think it is a good thing to have this tool, because this actually didn't work before, or at least they didn't have this data available. I was thinking, well, it'd be a lot better if the students just knew if they were cleared or not, and they go and fix that if they wanted to fix it, and so on and so forth. So that's what the tool is here now. So you see, before class, you can check and you'll know what that piece of paper is going to do. Now, I'm still going to do that piece of paper, but you can do this in advance, and I think this is a good thing. Okay, so the guides, this is kind of, and the big part of the guide is right up here. You go onto My Access, you go into your academic profile, under your profile, and you can find this. Okay, so here is what it will look like, and you might notice that they actually have John Doe on both of these forms, but these are different John Does, because over here, oh damn it, I thought they were different John Does. They're the same John Doe. This, I don't like this form, but anyway, the idea was that your form will either say not cleared here or it'll say cleared. I actually thought these were different ID numbers, and I had a pitch for that. But anyway, so you can go and you can check if you are cleared or not cleared. And again, previously I talked about what all this means, and I've talked about it more than I sort of want to, but I'm making you aware of this new tool. Okay, so I'm going to pause in case there's any questions or comments about this. I'm going to count to 10 Mississippi, and if nobody asks any questions, we'll go on to something else. Okay, that is good. And no one asked any questions, which is fine. Now I'm going to go back to this thing. Now I want to talk about individual questions and group answers. Um, and this wasn't so much an issue in differential equations, but it actually was an issue in another class, so I want to be clear about this. Um, Sometimes I will get a question from a student, and I will think, oh, this is just a question from that student. In fact, I will give you an example. And this is a student that I had in discrete math, but his question really was a one of. And in discrete math, we do a lot of proofs. And so this student wrote to me and said, hey, I've got these books that I'm working through on proofs, and I'm watching these videos and things like that. How much time should I be studying these proofs versus studying the discrete math? Now, that's kind of a one-off question because nobody else was asking me that question, and that student was being extremely diligent. But my answer to that student was, I think you will get enough about proofs for now, focusing on discrete math. So just focus on discrete math. You can read those other books later as you do it, but don't read it in parallel with discrete math. Focus on the task at hand, which is discrete math. I think that was good advice, and I didn't have to do that with everybody because a lot of people are, you know, not inclined to do extra reading and stuff like that. But there are other questions that people will ask um, that I'll read the question. I'll say, oh yeah, that's something that ought to be shared with everybody. And I'll just tell you something. Although the student actually was asking me a question, but it was really a question that I thought they should come to my office hours and ask me during my office hours. So anyway, what I did in answer to that question is I'm happy to have email dialogues with you about questions, but they are probably much more fruitful if we have such a thing, as face to face. We have a whiteboard or something, and we can talk and solve problems that way. So anyway, the idea of so often what I will do is I'll get an individual question. I say, oh, maybe there's a bunch of students that have that question, and so I will send out a group announcement to everybody about that. And when I do so, I think I've answered the individual question with the group answer. And it turned out that's something that's useful for students to understand. So I wanted to mention that. In all the classes I am teaching, my expectations are that you are responsible for what's in the videos and what's in the classroom material. Now, I realize that, and I mean, I know you guys are busy. I know I am busy. I know COVID sucks and causes all kinds of goofy stuff to happen. So I'm not intending to be unreasonable with this, but like I got out of my meeting and I had like 2 minutes or something to, oh, post some videos. So I sent videos to you uh, not very long before this class was happening. I am not expecting that you drop everything and you can watch and learn those videos. I think you should take your time with those videos and things like that. So I'm not expecting that you'll have them immediately in hand, but also I work very hard to have what's on the videos not to overlap exactly with what we're doing in the classroom. And maybe someday I'll stop posting the videos. I don't know. But anyway, that's what's going on. So my expectation is that you're looking at both of them and maybe even reviewing the BCM videos. And and I don't actually know if it was in this class, but one class said that they actually found the recordings of these videos to be useful. And could we do that when we got into the classroom? And I'm still looking into that. Technically, it's a different thing, and I have to think through that. I would like to accommodate that student's request, but I'm not sure how to do that. Okay. Um, Another student was, saying, I need to meet with you. And by the way, I am very interested in accommodating students, and I often have special meetings. In fact, the meeting that I had today was a special meeting with a student. And again, I wish the student had been able to come to my office hours, but the student either didn't understand my office hours or whatever. But I do have office hours, and they're in the announcements, and I actually am there. Now, I'm not staring at the Zoom screen, and so don't worry and say, oh gosh, Jim is probably lonely. I should go visit him. That's not necessary, because what I do is I open up a screen that's the Zoom office hour. I throw that over in the corner. If nobody's there, I do some work. And actually, doing work is good for me in several respects. So I do it. But anyway, if you have needs to meet with me, that's great. We can have special meetings that we have to schedule. But the office hours are there, and there's quite a few office hours. So anyway, that's what I've got with that. Okay, now what I'm going to move into is the polling segment of this. So I'm going to stop sharing, and I am going to go, I need to find Blackboard again. Here it is. And I'm going to look at the students in the class, and I'm just going to go down the list, and this is in alphabetical order. I do plan to call on everybody and check in how you are. And again, what Jesse and I are all about. I don't know if anybody went to Jesse's thing. In fact, here's what I'm going to say. If anybody did go to Jesse's thing, if it's happened already, if they have anything they want to say about it, they can. Again, I think that can really help answer a lot of questions. And if you go in with questions, Jesse knows how to answer them. And if you don't go in with questions, Jesse makes up problems. He prepares for that. And so that's good. Okay, so Daniel Johnston, you are the very first person here. And by the way, Daniel is, I think, the only one in this class who has his webcam on. I do appreciate that. And by the way, one of these days I will, and again, everybody doesn't have to, I actually have a webcam here, but it only works on Zoom for whatever reason, and it gives me a scrambled picture, and I haven't debugged it. And you might say, why don't you throw it away and buy another one? My daughter bought this for me. And so, it's kind of has sentimental value. Okay, so anyway, Daniel Johnston, three things. First of all, how are you and yours? Have you been able to engage with Jesse Hayes Carver at all? And no is an okay answer, but yes, it could be good. And then the third thing is, do you have any questions or issues you want to raise with me or with the class at this time?
I'm doing well.
Good.
I haven't really tried to go to tutoring. Haven't seen the need for it yet, not to say that I won't. And as for questions, the on one of the problems on the video, the one where you didn't give us a solution, I'm just trying to figure out how to get started on it.
Was that the Bernoulli problem, or was that something else?
It was
Or
the
was that
embedded
the
quiz.
LSA?
I'd likely say it was the LSA. The video is the 14th one in the playlist. That makes a difference.
Uh, I could look that. I'm going to guess that that was a Bernoulli thing, and maybe I started the problem. And let's pretend right now it was the Bernoulli thing, okay? And if it was the Bernoulli thing, then I think we'll talk about that enough that you'll feel comfortable at least on how to get started. If it wasn't the Bernoulli thing. If it and by the way, even though and I know you use the phrase tutoring, and I'm not upsetting or not trying to, let's see, it was the embedded quiz. Oh, I'm not expecting you to do that embedded quiz, but I'll tell you what, how about I'm going to ask you later if you can write that problem down. Okay.
I was
And
just ending the previous class time before trying to figure it out.
well, no, just you can ask me, okay? And I will talk a little bit about the embedded quiz and things like that. So, Daniel, I plan to return to you after this is over. I don't want to do that right now just because I want to, some of these people might not have anything at all. I do want to say a comment though. Just meeting Jesse is a useful thing. So if you just drop in and say, hey, I wanted to meet you, that's okay. And you can leave and drop in and out. And it doesn't mean you're a weak student. In fact, I will tell you, sometimes Jesse actually challenges the students with more challenging problems than the ones he thinks I'm asking and things like that. So feel free to drop in, and it doesn't mean that you need anything. In fact, Jesse has helped a lot of good students. So okay, so then Daniel, please have that problem later, and I will try to remember that the very first thing after this, I will say tell me the problem, and I'll make a whiteboard, and we'll talk about it a bit. Okay.
All right.
All right, so that can be good. And so I think we're ready to go on, except I will return to you. Okay, I'm moving on now to Jenny, no, excuse me, Danny Janiak. Danny, how are you and yours? Do you have any questions you want to share and with me and anything? By the way, Jesse tells me, now Jesse does not tell me who showed up. But Jesse will say, "Hey, nobody showed up," and that's it, if that's the case. But sometimes I say, "Hey, I had 3 people," and I don't ask him who they were. I just say, "Oh, that was good," and so we have. Okay, so Danny, how about you? How are you and yours? And do you have any questions for me?
I'm doing well, thank you. I don't have any questions.
Okay, that's okay. It's good if you have questions. It's fine if you don't. And I will tell the story about the embedded quiz too. Okay, let's go to Eleanor. Eleanor, how are you and yours? And do you have any questions or comments for the class or me?
I'm doing well, thank you. Um,
Good.
I do have a question regarding the LSA. Do you happen to know what video it is on, or like where I just don't know where to find it?
Okay, I will find that and I will post it separately. Okay. My guess is that my guess but this is a guess, is this in the separation of videos, but you shouldn't have to scramble around for that. So I will find it, okay? And you might say, oh my gosh, I don't have as much time to work on it. You won't need that much time to work on it. And I think I'm going, in fact, just in the same way with Daniel, I'm going to talk about that one. I'll talk a little bit about the LSA one because some students might say, oh, gee, you're expecting me to know more physics than I know. And so we'll talk a little bit about that, and I will strive to find it. Okay, and I will post it for you. Anything else, Eleanor?
That'll be it. Thank you.
Okay, excellent. Fazan, anything? First of all, how are you and yours? And anything you wish to share with me or the class? And sometimes Fazan sends me a chat, and he does this time too. He says no questions, and I'm taking that to mean he's okay as well. Okay, now Jonathan Michael, who is my sounding board this time, do you have anything? Well, first of all, how are you and yours? And is there anything going on that you want to share with me or the class?
I'm doing well, and I don't have
Good.
any questions about anything at the moment.
Okay, excellent. Your questions are always welcome. That's what learning is about. Okay, then we're going on to, we're getting near the end. Rohan, and Rohan, like Jesse Hayes Carver, has a hyphenated last name. But anyway, Rohan, how are you and yours? And do you have any questions or comments you want to share with the class?
I'm doing well right now. I do not have any questions at the moment.
Okay, that I will take that to be good. And again, it's good if you have questions. And then last but not least, Victor, because V is near the end of the alphabet. Uh, Victor Campos, how are you and yours? And do you have any questions or comments you wish to share at this time with me or the class?
No, I'm doing pretty good. I'm happy with where I'm at. So, yeah.
Okay, that's good. Okay, now I am going to. I need to think about what I'm doing here. Okay, so I am going to share a whiteboard. And this showed up as an embedded quiz. And by the way, sometimes a video is, and by the way, I've really stopped doing this, okay? And I was not trying to be mean, but I was trying to figure out what worked, and this doesn't work, okay? So back in the day when I made that video, and COVID was newer back then, I thought, oh, maybe I can, and not trying to trick the students, but to encourage the students to watch the videos promptly, I would embed a quiz in the video and say, oh, do this and turn it in. And, and the students viewed that as entrapment, and they didn't like it. And everybody says, oh, can I turn it in late? And all this stuff. So I decided that wasn't a good idea. Now, so I'm not asking you to turn anything in, but it's still a legit problem. So I am going to ask Daniel to kind of read for me the problem, and I might not write it exactly the way you read it, but I want to give you a leg up as to how you would approach it perhaps. So go ahead, if you will, and please just kind of read the problem as you encountered it.
In parentheses, y minus the root of x squared plus y squared, close parentheses, dx.
X squared, and I think the way I heard you was that way, yes?
Yep.
Okay.
Close parentheses, dx minus x dy equals 0.
Okay, now here's, and by the way, this is useful in getting started, but I'm going to be talking about something that is sort of coming up. So if you haven't watched this video, it may, be, let's see. So if I take the derivative with respect to y, and this was x squared times y squared, yes?
Plus y squared.
Oh, that's plus y squared. Okay. All right, so I need to erase that just a little bit. And it was plus y squared. Okay. All right, and let's see. So I was thinking, and I've changed my mind now that we've changed this. And so I'm erasing this part here. And I don't think I'm going to work the problem for you, but I'm going to give you the strong hint. Okay, so just working on looking at this, then what I see is that the exponent that's living on that term is a 1. And the exponent that's living on this term is a 1. Okay, now what we do is here, it's really not, it's not exactly a 1, but you see this is x squared plus y squared, and it's all the square root. If you take the square root of 2, it's 1. So what I'm thinking is that we can declare that this is homogeneous of degree 1. Okay, and the way we talked about that is if we replace y, now this is the definition, if we replace y with ty, And here we're replacing both x and y with ty and tx. So what happens is we get the square root of, this is tx, tx whole squared, plus, and then this is ty whole squared. And then you got the square root of that business, and then this is minus, and this would be tx to the first power. Okay, and you see what we're trying to see is, oh, is this t times, well, I'm going to say f of xy. And I don't think I did this notationally very well, excuse me. But over here, I'm saying that this thing up here, I'm going to call f of xy. So what I got down here is, I'm much better on a chalkboard than I am at this, but tx, ty. Ah, damn it, that looked like a first grader writing. Actually, I probably wrote better than this in the first grade. Okay, so if I put this here, this would sit up here, and that would be equal to that. Okay, so the theory goes is if something isn't separable, but it is homogeneous of a certain degree alpha, and in this case, alpha would be 1, and that means we replace x with tx and we replace y with ty. If that's the same thing as t factoring out of f of xy, it's homogeneous of degree 1, and that means that we can do a substitution to turn this into a separable differential equation. Okay, now and there's two ways that you can go. Okay, so either you would say that y is equal to vx, or x is equal to z times y. Now, so you're going to be doing this substitution, and you could say, oh, and this is the same thing as y over x equal v, and down here you could say that y is equal to x over z. And you don't just do that substitution. What you have to do is substitute for the differential as well. Now, I'm not going to write all that stuff, but I'm going to just pick the top one, and I'm going to say that, okay, so this says that dy as a differential is going to be v dx plus, and it's going to be 1. That's just going to be dv. Okay, so, and you in theory can either use the y equal vx or the x equals zy, but often what will happen is, and it certainly could happen, you're doing one of these problems and say, damn, I don't know how to do that integral, and maybe the other way would be easier, and there's no way a priori to pick that, so you just try something. Now I'm giving you open-ended time to take a test, and it's not super open-ended, but it's quite open-ended in the testing center. So you could go down a wrong path and say, oh, that didn't work, I have to go back and redo it, but that's just the way life goes. I would probably try this first one first and go through there. But when you do the substitution, you should end up with a separable equation, which you're going to be able to solve for v. Or maybe you can solve it for v, at least you're saying v is there, and then you're going to have to reverse the substitution back to this. Now, I don't know if that was enough, Daniel, of a foothold on this, or if you have some questions about this. I could plow through and do the whole thing. I'm not 100% sure that's the best use of our time, but what do you think?
I think knowing that the substitution exists and that I know what the substitution has to be is probably going to be a big help in figuring out what the heck it
Okay.
is.
Okay, but by the way, that is one of the skills that you need. I do have an exercise set, and I'll try to remember to do it, but I have to remember to do it, and then I have to go off and do it. But you see, one of your things is most of the problems I'm going to give you on a test or a high stakes assessment will be, hey, solve this. And you have to say, how in the hell am I going to solve it? And sometimes there's multiple ways to go. But this is an important thing because you need to look at this and say, oh, of the tools I have, what do I do? And I think I call this thing I put together, I called it mixed review exercise. And I'll try to remember to share this with you guys before we do it. Because you see, what happens is we will be studying homogeneous equations. And when we're studying the homogeneous equations, everything is a homogeneous equation pretty much. And so you say, oh, I'm good at this. But it's another thing to look at a naked problem that could be any number of things and say, oh, and this is what I'm going to do. So anyway, we'll practice that. And I'm going to then pretend, Daniel, that at least for now, I've answered this question. Please understand, I gave up that idea of embedded quizzes. It was a bad idea, and so I'm not repeating it. Although I guess I reused the video and I stuck it in there, so that probably was confusing.
Yeah,
We
makes
good,
sense.
Daniel?
Yeah, I'm good. I'll
Okay,
solve
all
it
right.
in my off time because it's a good problem for me to work on.
Yep, so, okay, so that is a good thing. Now I am going to, and I'm not sure, well, I'm going to say this is a good use of time, and I don't want to ignore, I think it was Eleanor's question or comment. I gave you a problem about a snowball, and I have to go find it. But basically, you had a snowball melting, and in a sense, that is a little bit like the it's a little bit like the oh, let's see, what do I want to say? It is a little bit like the radioactive decay, but not exactly. Because you see, and you might recall that the radioactive decay thing that we did in the very first class, the physics drove us to say that dy dt was proportional to y. And this had to do with carbon 14 and stuff like that, and we solved this, and this was something I solved. I do expect you to know how to solve these radioactive decay problems and things like that, but this was a snowball. Okay, and you got a snowball. I know you guys are engineers, but there used to be a book called Fear of Physics that opened with a joke, and it is risky telling a joke, but I'm going to tell you the joke anyway. The way and this really was the start of the book about fear of physics, and it was on one hand it was making a little bit of fun of physics folk, but also it was there was a lot of good stuff in the book. And in fact, I often, I don't know if I'll do it here, but often when I'm teaching a class that involves some physics, I will in fact borrow stuff from that Fear of Physics website. It's kind of a cool site. But anyway, so the story goes, and by the way, at the end of this, feel free to tell me never tell a joke again. But anyway, there was this farmer, and the farmer had milk cows, and he wanted to improve the production of the milk cows. And so anyway, he hired an industrial psychologist, a physicist, and a musician. And he said, how can I make my cows give more milk? And the magician said, oh, you should play classical music in the background, and that will make them better. And by the way, there have been studies, I don't know if I believe them or not, but there have been studies that if you listen to classical music, namely Mozart, that people do better on math tests if they have that classical music going. And I do listen to music when I work. For other people, I think that's probably very distracting, but I do listen to music when I work, although it is not always classical music. I have some eclectic taste. But anyway, so the guy said, oh, you should be playing music in your barn and classical music, and the cows will give more milk. And the environmental guy said, you know, what you really need to do is paint your barn inside a nice green, and the cows will be energized by the green and they will give more milk. Then he asked the physicist, okay, so what do you want? And the physicist went up to a chalkboard and started drawing a picture, and he says, let's assume the cow is a sphere. And that's the joke. And maybe you didn't think that was funny at all. I'm sure maybe you didn't, but I still think that is funny, and that's actually the way it goes. Anyway, the reason I thought of that right now is, you see, this problem is about a snowball, and so I say that a snowball is sort of like a sphere, sort of a sphere. So for the purposes of this, and you can't see what I'm writing until I'm finished writing it. That's the way this Collaborate Ultra works. But anyway, you should assume that the snowball is pretty much spherical. And in fact, physicists will assume that cows are a sphere. When you're solving a problem about the Earth, you assume the Earth is a sphere. It's not a perfect sphere, but you assume it's a large sphere. So you're talking about a snowball. And so one of the equations that is of interest is this one, that the volume of a sphere is 4/3. This is pi the number, and this is r cubed. And maybe you know that formula and that's ingrained in your mind, and maybe it's not. Now, the surface area of a sphere, I would just say SA, and I don't know, maybe I'm being too mathy, but the surface area, actually, if you think about it, is like the differential of the volume, because it's say, oh, if the volume changes just a little bit, that's actually the surface area of a sphere. And that formula is true whether you want to think about it that way or not. So this is going to be 4 pi r squared. So the evaporation, which is what we're talking about in the problem, and you got to think about this a little bit, but the evaporation only happens on the surface of the snowball. Okay, and so I give you some information, and you want the snowball to go to 0, so you want the volume to be 0. So this is the, let's see, I need to think about how I'm going to do this. If we just talk about the volume of the snowball, the change of the volume with respect to the radius is proportional to the surface area. Because you evaporate off the surface. And Eleanor, I'm not necessarily calling on you. I'm just saying, is this helpful?
Yeah, because I didn't really know what the problem was before, but now I do. So.
Well, yeah, and I'll find the problem and post it for you. But it's something like I give you a snowball and I say, oh, the snowball is, I'm making up these numbers. These are not the right numbers. But at time t0, t equals 0, at that time the radius of the snowball was 10 centimeters. Which you actually can make a snowball that's 10 centimeters. That's not very enormous. Actually, that's about 5 inches in diameter. And then I tell you a certain amount of time, like in 20 minutes, it melts to oh, I don't know, I'm making up this number, 4 centimeters. When is it totally gone? Okay, so it's sort of like sort of like the problem we did once upon a time before, but it's not either, because the physics is a little different. It's more like this. And the radius is actually a function of time. So I mean, I think I've given you enough hint on this to get started. Okay. And I will, Eleanor and everybody else, I will you know, look that up so we can find it, and things like that. Okay. All right. So that is that. Let's see. Something's going on here. What is the symbol before? I'm going to look at that comment again just to get what is the symbol before the D?
The 4.
Before the 4. That's K. That's a constant of proportionality. And you can figure out what the constant of proportionality is. It's supposed to be a K. You can figure out the constant of proportionality based on the information that I've given you in the problem. Okay. All right. So let's call that good. Now you might think, am I worried about, you know, spending time doing that? No, not at all. I mean, I think there was learning went on. There's some interaction. That's all good. And to tell you the truth, you see, since I'm holding you responsible for the videos as well as this, you know, what we do in class is a little bit of perhaps gravy. Okay, so what I'm going to do then is I'm going to go and we're going to talk a little bit about the Bernoulli equation. And I might not be doing these slides in the order in which they show up, and that's okay. I think I want to talk about Bernoulli first because I think I started talking about that last time and then I went away. And Bernoulli is like a really famous mathematician. In fact, there's a Bernoulli family, and they're all kinds of brothers and nephews, and you know, they were a very dysfunctional family too. They sort of would you know, criticize each other's research and stuff like that, but they really were they were very smart. Okay, so anyway, let me find my Bernoulli things. Going down here. Okay, and so here is now, and let's see. I think it's Jonathan, you're keeping me honest. And again, just if you don't see a PowerPoint slide, that means I fucked up. But anyway, so here we go. In mathematics, an ordinary differential equation is called a Bernoulli differential equation if it is of this form. And one of the critical things that will trigger it being of this form, and by the way, pretend that y to the nth wasn't there, this would be a linear first order differential equation, which should be your favorite kind of differential equation because you got a clear way to solve it. You got the integrating factor, you just romp through, you solve it, it is all good. And I will ask you on both the midterm and final assessments in this class, I will give you first order linear differential equations. Now they might be a little bit in disguise or something like that, but this looks like a linear first order differential equation, except you got that y to the nth there. And you might say, is that a big deal? Well, and the answer is heck yes, because that makes this into a very non-linear differential equation. And there are, I'm not prepared to talk about the applications of this, but there are big applications of this as well. This arose in some engineering problems and stuff like that. Anyway, it says some authors allow any real n. I think our author allows any real n. So that n could be any number, and in fact, so it could be the square root of 2. Now that might make the problem nasty, but it could be the square root of 2. It could be 1/2. It could be things like that. So when we're looking at this, we're going to realize, oh, this is a Bernoulli problem, and then how do we solve this? And a key substitution on the Bernoulli problem is this. And once you realize it's a Bernoulli problem, you can just say, oh, well, I'm going to do that. Actually, okay, so this is the substitution that you make, and I started to write it here this way, and oh, I'm just gonna, well, let's see. I don't, oh wait, I do have the drawing tool on this. Hold on. Sometimes I don't have 365, so I should be able to draw here. Okay, and so if you have Bernoulli, and if I'm telling you something's there that you're not seeing, so we let z equal 1y to the 1 minus n. Now you have to flush out this entire substitution, but this is your mainline substitution. So you're going to replace the y by a z. And what will happen if you do this, so if you truly have a Bernoulli equation and you make this substitution, and in my video I may talk about why that's true, but I'm not going to ask you to prove why it's true, and you just know, oh yeah, this works, that's a Bernoulli equation. So that means that d z dx. So you see I still have the same independent variable. So dz dx then has to be, and this is going to be, then it's going to be 1 minus n, and then it is going to be y, and then this is going to be, you subtract 1 from this. I mean, we're taking a derivative. So it's 1 minus n. You take 1 from the exponent, so this is minus n. And then this is dy dx. Okay. And okay, and by the way, this substitution here, I mean that's what we have, but that says that let's see, so z to the 1 over 1 minus n is equal to y. Okay, so what I'm going to do is I'm going to use these substitutions into this equation up here. And you see, I don't have to worry about x because that's just p of x. Don't have to worry about q of x. So the only thing I'm changing is the y prime, the y, and the y to the n. And so that will change this into a linear equation. And let's see. That's not what I wanted to do. Hold on. There we go. Maybe. This will change the nonlinear V equation, Bernoulli equation, into a linear equation. I'll show you what, so you can see what I've written. And so that's going to be true. Okay, so this will change the nonlinear Bernoulli equation into a linear equation, and then you solve it. But you see, the original problem, you wanted to know what y is, so you have to invert the substitution at the end. Okay, and I'll maybe make a note like that. I don't know. Yeah, I guess I will. Okay, and we know how to solve. So we solve the linear differential equation, and then return to the native. Damn it, that wasn't supposed to happen that way. I got some kind of a security thing going on here that I don't want. Okay, yes, I have trouble with my passwords, but I don't want to do that. I don't want to do that. I don't want to do that. I'm hoping eventually return to the native variables. and I will click somewhere and you'll be able to see what I wrote. Okay, that's the approach. Now, really the only thing you have to remember is what a Bernoulli equation looks like in this original substitution, and you can figure out the rest of it. Okay, so I'm going to ask you guys, please, to solve a problem here. And wow, I don't know which one necessarily to do, but I think I'm going to say, hey, everybody tackle problem 15. Now, and by the way, 15, and you might say, oh, that's not exactly the Bernoulli equation to start with, but what you're going to do with that leading x is you're going to divide all the way through by x. And then you've got y to the minus 2. So your substitution here, I guess I can draw on this. So your substitution is going to be, oops, that doesn't work. Let me try something else. Okay, so I'm going to say, I don't know how to do that. Here I'm doing this, I guess. So first you divide all the way through. In fact, I'm going to make this like really small. Okay, and that now I can write over here, I think. Okay, so I divide all the way through by that. And so then here is what I have. dy. Okay, dy dx is equal to, or no, it's not equal to, it is plus 1 over x times y. And then this is equal to, and now I did divide by the 1 over x, so this is 1 over x. And this is y now to the minus 2. Okay, so now it does genuinely look like a Bernoulli equation. And so I say, oh, so the substitution I want to do is this one. I'm calling it z. You can call it whatever you want, but I'm calling it z. So z is equal to, and this is y to the 1 minus n. Now here, 1 minus a minus 2 is y cubed. Okay, now I think that's enough, and we're going to work until about quarter past. Then I give you a break because listening to me for more than 75 minutes at a time is cruel and unusual punishment. But we're not quite to there yet. So I'm going to suggest you give this a go for 10 minutes. Try to solve it. And again, I kind of told you what should happen. And then we'll come back together and we'll look at a solution, and hopefully all before the break. So I'm giving you about 10 minutes to work on this. And by the way, that's exactly how I'll do something in class. I'll talk a while and I'll say, hey, you guys try this. And it is to your benefit to try this. Some students might say, oh, I just will do my cell phone, or I'll go get a cup of coffee or something like that. It really is to your advantage to try this because you're thinking about the problem. So, okay, so please give this a go, and we will return and talk about 15 in a bit. So everybody go. I'm going to stop sharing, so make sure you've written this down because I'm going to prepare for when we come back to talk about a solution. Okay, so please go.
Are we coming back in 10 or 15?
You're coming back in 10. At 2:10,
Gotcha.
I will say, hey, I'm not saying time's up. I'm just saying, hey, let's talk about the solution. And wherever you are, it's fine, but we'll pick it up there. So at 2:10-ish, we will come back and we'll talk about the solution for 5 minutes. Then we'll take the break, okay, at 2:15-ish. Okay, let's see, we've hit 2:10, so let me, I'm going to be sharing again. I'm going to share my application screen. Now, maybe you solved it, maybe you didn't, and it's not just about being fast, it's really much more about being right. I'm going to find my application screen again somewhere. Here it is, okay. And so that was the problem. And this is, well, I guess sort of like the outline of a solution. And so, in fact, I'm going to change this screen just a little bit, the layout, so I can move this stuff around more effectively. Okay, so I'm going to, oops. Oh, I see what I'm doing. I'm drawing on it instead. How do I stop drawing? Anyway, okay. Well, okay, so we're letting y equal, excuse me, w, and I know I was doing z, and you can call it whatever you want, but w is equal to y cubed. That means dw dx is going to be 3y squared dy dt. That is the chain rule. And then if I solve for dy dt, and that's actually supposed to be dy dx, damn it. It's supposed to be x, not dt. Let's see, so what's happening here? And it's supposed to be x up here too. Okay, so we get that's 1 over y squared. Dy dx is dy. So anyway, if we do all of this substitution, what we should then get is this expression right here. Now, you have to realize that you're multiplying both sides by y squared to get rid of the y to the minus 2, and so you're doing all of that. But anyway, you should see your way to clear to get to this, and this is then going to be a linear equation in w. So we'll solve this with an integrating factor, and the integrating factor is going to be e. I guess I could review that too. So the integrating factor is going to be e to the integral. This is 3 over x dx. Okay, now that 3 is going to pull out, so if you think about this for a while, that really is x cubed. So you multiply all the way through by x cubed, and what you're going to get then is x cubed dw dx plus, and then this is going to be 3x squared w, and that's going to be equal to 3x squared. Okay, so then what you realize is that this is a perfect differential. This is the derivative of this. So we integrate both sides, and my machine is acting up. It's goofing up. And I'm going to pause right here. I think you guys can finish and fill in the blanks. And then the last step is you do have to go back to the native variable, so you have to do y. And so what you're really doing is you're going back, and everywhere you got a w, you're going to put a y cubed. Okay, so I'm pausing, and I do want questions here. If there's questions, I will give you your full 10 minutes of break, so don't worry about, oh, I'm eating into the break. So I'm going to count to 10 Mississippi to see if there are questions. Okay, I hit 10 Mississippi and no one asked any questions. Now there's a whole bunch of Bernoulli problems, and I am mindful of time, and I am going to be giving you the break in just a minute. That's not the one I want. Where was it? Oh, here's a whole bunch of other Bernoulli problems that you could do, and you see that y is going to be different things in those, but I think that's probably enough. So when we return, we're going to talk about something else when we return from the break in 10 minutes, and I'm going to call this 2:16, and that means by my clock at 2:26, I'll start talking again, and we'll talk till the end of our time together. Okay, we're on break now. Okay, it's time to, I guess, reconvene. And so now we're going to talk about something else. And I'm going to spend a little bit of time talking about exact equations. And we're going to solve a couple of exact equations. And again, we're going to be working until, let's see, 2:50 gives you, you know, the right amount of time and things like that. So that's sort of our terminus. This is the shorter end of the thing. Now, I'm not repeating the lecture that I put in the videos. And so you might say, well, you're being short on detail here. Well, I got good detail there. And I also am going to be talking about different examples here. And this is one of the things that if we had done that big old calculus review, we would have reviewed all this. But now I'm just asking you to remember it, okay? And also during the break, PowerPoint died on me, and but that's okay because I have ways of continuing to work, so it's all good. Okay, so I'm going to, oops, I was supposed to be sharing first. I need to go back and do the share thing. Okay, so I'm going to be sharing my application screen with you. And Jonathan is making sure that you'll see it in a bit. You can't see it yet, but it's going to be here. Okay, and now I'm just going to be pointing at some things here. And I think you can see my cursor. I hope you can. Okay, so what I'm talking about here is f of xy, but this is capital F of xy. It's an implicitly defined function equal to c. Okay, so this means that this is a, you know, a three-dimensional thing. I got two variables, but anyway, this is an implicitly defined function. But one of the things that we learned in Calc 3 at the College of DuPage is we learned how to take the derivative of this with respect to x, and the derivative is going to be, you're going to have the partial of capital F with respect to x, plus then you have to use the chain rule because we're assuming that y is a function of x. This is a partial of f with respect to y, and then this is dy dx. And then that's equal to 0 because the derivative of the constant is 0. So I just differentiate this function with respect to x and use the chain rule, and I get this. But this is the same thing as this if I simplify it. And so what I'm going to get is the partial of f with respect to x dx plus the partial of y with respect to y dy. And that's what's going to be equal to, and in fact, in the problem we were talking about, it was equal to 0. And if you're thinking about this and you say, well, the partial of f with respect to x could be a function. This is capital M of xy dx, plus this is n of xy dy, and that's equal to 0. So let's just go through and we're going to solve an exact differential equation without even calling it that. Okay, so here we go. This is called example 1. And Jonathan, I'm not trying to pick on you or anything, but can you see this example 1 down here?
I can.
Excellent. Okay, so I'm going to pretend that this is good for everybody. Okay, so we're going to start with saying, oh, here is a differential equation that we would like to solve. And you could just pretend, oh, this might be on a test someday or something. Okay, so this is a differential equation. You might start looking at that and say, well, it's not separable. It's not, you know, things like that. And the reason is, and it's not a Bernoulli equation, and you think about all those things and you say, gosh, what is this? Well, we haven't talked about it yet, but this is going to be what I call an exact equation. Okay, now, so what we're going to do though is reorganize this. And so we're going to cross multiply this dy times this guy and this numerator times the other guy, and we're going to put it all on the same side. And what we end up with is 2xy squared plus 1 dx plus 2x squared y dy is equal to 0. Now this is a different kind of differential equation that we have. And we could organize this different ways too, but this is actually a very good way to approach this problem is right here, because we're going to observe that this is an exact differential. Because if I go down and I start thinking about the function that is called f of xy, it's down here, this one, f of xy equal x squared times y squared plus x. If I take the partial of this with respect to x, I'll get 2xy squared plus 1, which is exactly what's sitting there. And if I take the partial of this thing with respect to y, I will get 2x squared y, which is exactly the thing sitting there. So if you think about that, you say, oh, damn, that means this thing is an exact differential. This is the derivative of that. And of course, that means what I can do is I can say that, and you see, and if this was equal to 0, which it was, go all the way back up here, you see it's equal to 0. So I'm saying, oh, the differential of this is a constant, is 0. So that means if I integrate this, and if I integrate this, I get x squared y squared plus x. That's equal to a constant. And so this is the solution. And it is an implicitly defined solution, but that's still a solution. So you see, that's actually a good thing. And that was a good, I think, introduction without talking about definitions and things like that. Okay, now I'm going to continue to talk. And here's the form. Okay, so so if you encounter a differential equation like this, or that can be put into this form, and this form is m of x dx plus n of y dy equals 0, then it might be an exact equation. Now it's going to be an exact equation if you can find a capital F of xy such that the partial of f with respect to x is this m character, and the partial of capital F with respect to y is this n character. And if so, you got an exact differential equation, and you can solve it exactly the way we did in example 1. Now, this actually does come up in applications sometimes. So that's what it is. But you have to say, well, how are we going to know if this is an exact differential or not? And we have a test for exactness. And this test, actually, some people call this test Clairaut's equation. But it's not the Clairaut's equation that we're studying. And you did study this in your Calc 3 class, okay? And so this is the test for being an exact differential. And maybe you remember it, maybe you don't, but we're talking about it now. So I'm going to quote this theorem that is called Theorem 2. So suppose that the first partial derivatives of m and n are continuous in a rectangle R. And by the way, if you don't have that continuity, you can come up with weird counterexamples to this. But usually that's the case because nature is usually continuous, and I'm not trying to trick you. If I were teaching this course at Princeton or somewhere like that, and not trying to trick you, but we talk about different things and we look at the proofs and why do you need that, and things like that. But here we're focusing on just, can you solve the differential equations? Recognize that this is it. So suppose this is, then this is an exact equation, and this is if and only if. Now again, this continuous second partials are an important thing, but this is an exact equation if, and this is what you have. Now, and I will tell you that this does confuse someone's students, so be a little bit careful. The partial of m with respect to y has to be the same as the partial of n with respect to x. Now that's not the same thing that we had with the exact, and basically what this is saying is that this is if and only if. These are really the second partials, and you're really saying, oh, the second partials, it doesn't matter which way you do it. So you see, if this is the case, then it is an exact equation. So you do want to keep this test in mind, and you do really want to write this carefully. So what you maybe want to do, I would advise thinking about it anyway. So you got m dx plus n dy. This is the test to see if it is exact or not. And then we're going to solve it if it's exact, and we'll talk about how you solve it if it is exact. But you have to first of all say, is it exact or not? And again, I haven't written any of your tests or anything else, but I could say, hey, is this an exact equation or not? Well, this is what you would do, and you would see if you have these two things equal, and if they are, then it is exact and you can solve it. Okay, now, so and we could just think about our example in one. This is what we had. So if we took the partial of m, which is the thing I'm waving my my cursor under here, the partial of m with respect to y is going, and the partial of this one are both 4xy. So you see, we would have known that from this. Okay. And I'm trying to think, I am very aware of what time it is. I think I'm not going to prove this theorem with you. I might prove it. I might have proved it on the video. I think I did. And by the way, from a historical footnote, this theorem was first proven by Leonhard Euler, who was perhaps the greatest mathematician. People argue about such things, but I would vote for Euler. And Euler will come up many times in this course. And there he is coming up right now. Okay, so let's go to this, and I'm going to read this to you. And I think I go over this in some examples in the videos, but anyway, okay. So if m dx plus n dy equals 0 is exact, then we know that the partial of f, which is the thing we're trying to find, with respect to x is m. So we can integrate this with respect to x to get f of xy is equal to the integral of, this is m of xy dx, and then there's a constant. But the constant of integration, if you're integrating with respect to x, the constant is really a function of y. And maybe you guys remember this from your Calc 3, but anyway, it's a function of y. So you say, okay, well, but we need to figure out what g of y is. So to determine g of y, we take the partial with respect to y of both sides. Now, if we take the partial with respect to y, that's just going to be g prime of y. So you get g prime of y is equal to something. Then we can integrate g prime of y to obtain g of y up to a numerical constant. And if it's an initial value problem, you can figure out what the constant is. So we substitute g of y into, I call this equation 11, I guess. That gives us f of xy. So the solution is given implicitly by f of xy equal a constant. And alternatively, you could have started with the derivative with respect to y and worked through that. Okay, now I got to tell you that I don't think memorizing stuff like this is really useful. I think you do want to remember the test for exactness, but beyond that, you just kind of follow your nose. So let's look at a problem then. Again, I'm watching carefully what time it is. And so here's a thing called example 2. And this, I don't think these were the examples I did in the video. Okay, so these are different examples, and they definitely aren't the examples from your textbook. So you got a lot of examples that you can look at. Okay, so let's start with this problem. This problem is not laid out in a tricky way. And so you got an m here, and you got an n of xy here. Okay. Now let's test to see if it is exact. And by the way, if it's not exact, you have to do something else. But if it's exact, you say, oh, this is I know how to do. So what we're going to do is, and remember now that this one is the partial of capital F with respect to x, but we're actually checking the derivative of m with respect to y. Now we're taking the derivative with respect to y. The only y you've got is in this first part, so that is 2x. And over here, you're taking the derivative of n with respect to x, and you get 2x. So you see, oh, this is exact. So that is good. So now what we're going to do is we're going to do exactly what we said that we would do. So what we're going to do is we're going to integrate this m, and remember this was m up here, with respect to x. Okay, and so we do that. Now, you're going to do it term by term. So when you integrate 2xy, but you're integrating with respect to x, that's going to be x squared times y. And then here's a minus sign. This minus sign is that minus sign. And then you're integrating the secant squared of x dx, which is known to be the tangent of x. And then there is a constant that happens here, but your constant is going to be written as a function of y because we are integrating with respect to x. So this is what we have for f of xy, but we don't know what g of y is yet. But now what we're going to do is we're going to go back and use our other equation, and we know that, oh yeah, but the partial of capital F with respect to y has to be this, x squared plus 2xy. So what we're going to do is we're going to take the partial of this, which is f of xy, and we're taking it with respect to y. So you see this is going to be x squared. And then here you get, this is a function of x, so when we take the derivative of y, that's 0, and that is g prime, and that has to be x squared plus 2y. So you see we have x squared plus g prime of x is equal to x squared plus 2y. Well, if you look at this, you say, yeah, but I can subtract the x squareds from both sides. So g prime of y is 2y. That means g of y is y squared, and there is a constant, and that constant, so you could say this is y squared plus a constant, but you have f of xy is equal to x squared y minus 10x plus y squared, and you do have to have it's equal to 0, and so there is the implicit solution, and you do have to do that. Now I'm going to pause here for a count of 10 Mississippi, just because I did go through all this rather quickly, and people may have questions on that. Most of it is on the screen right now. So I'm counting to 10 Mississippi in case people want to ask questions, and just jump in and ask your questions if you have them. Okay. We have 7 minutes left, and I'm going to ask people to, I'll see if I can make a PowerPoint slide of this. Maybe I can, maybe I can't. This is the problem we're going to talk about. And the first thing you want to do is check to see if it is exact. And let's see, cancel, I don't know. I'm trying to paste this somewhere. I think I'll open a Word doc to paste it in. This is this stuff down here isn't working so well. I'm just going to go here and I'll paste it and see if I got it. Okay, there. So there's the problem that you want to test. So check to see, is it exact? And try to solve it. Now, I didn't give you very much time. We've got 5 minutes. I'll give you 3 minutes to work on it. Then we'll come back and we'll talk about the solution. But everybody, please give that one a go. It is 1 plus e to the xy plus x e to the xy. And we got x e to the y, or x e to the x plus 2 dy, all of it's equal to 0. So test to see if that's exact and start trying to solve it. Okay, the time is probably up for giving you a solution. I am watching the thing. So let's look at the solution then. So if you take the partial with respect to y of m and the partial of n with respect to x, you get the same thing. That means it's exact. So we're going to integrate n of xy this time. Now, by the way, integrating this, we're integrating with respect to y, so you see that's just going to be a constant plus 2y. Now, if you were integrating with respect to x, and that's, by the way, that's why someone probably didn't choose to integrate with respect to x, because if you're integrating with respect to x, you would have had to integrate by parts, and that wouldn't necessarily be fun. So anyway, we integrate this, we get xe to the xy plus 2y plus h of x. Now we take the derivative of this, and that has to be the m of xy. So we set this plus h prime of x equal to the other side, and you compare notes, and you say, oh, that 1 has to be h prime of x. So that says that that is x, and we'll call it x plus c, and we can move the c around. So anyway, f of xy is going to be x e to the xy plus 2y plus x, and the solution is implicitly given by here is f of xy equals c. And now in this case, and this is a little bit different, but you can't solve explicitly for y, and if I had given you an initial value problem, you could have figured out what c is as well. Okay, so that's what happens here. I'm about ready to dismiss you, but I guess I'll count for 5 Mississippi if anybody wants to bring anything up. Okay, no one brought anything up, which is always cool. You got some videos, and in fact, the videos go further than where we are in class. I'm not worrying about that. This is the last time, and unless you hear something from me, we'll meet in a classroom the next time we meet. I'm actually looking forward to that. I hope you are too. And it is important for young people to be careful on weekends, and so please be careful. I'll look forward to seeing you next week. Take care, and we're dismissed. See you Monday. And I'm turning off the recording.